Welcome to another thrilling episode of Dave Does Math from Home. We are wrapping up Calc 3. This is the end of it. We've made it through flux integrals, and I'm very proud of you for that. Well done there. The last two sections we have are still about flux integrals, but they are shortcuts for doing flux integrals more simply and more easily. And there's two flavors of these shortcuts. There's a curl flavored shortcut and there's a divergence flavored shortcut, which is why we did section 17.5, curl and divergence. So we're going to use both of those. We're going to start with 17.7. And 17.7 is the curl flavored shortcut, which is, if I'm being honest, it's the much more sort of intense shortcut. This might not feel like a shortcut. But we're going to do it. It's good to be able to switch back and forth between the two modes of Stokes' theorem. So we're going to talk about that. It'll go pretty quick, I promise. We're just going to get directly into it. Stokes' theorem says that if you're doing the surface integral of the curl of a vector field, you can instead do the line integral around the edge of your surface. This only applies to surfaces that have an edge. So things like if you're doing like a half sphere, if you're trying to do like the end of our flux integral videos, we did the flux through a half sphere. If you have a half sphere like that, and that has an edge, the edge of that half sphere is a circle. So if the vector field you're doing a flux integral for is the curl of something, then instead of doing the surface integral, the flux integral through that surface, you can do the line integral around the edge. Figuring out when a vector field is the curl of another vector field is kind of a challenge. It's not like path independence where there's a really easy test where we can be like, yeah, here's how you figure that out and here's how you determine what the original function is. So this is honestly not often used in this direction. I think it's more often used in this direction. So instead of doing the circulation is a fancy word for a line integral that starts and ends in the same place. So if you're going around in a circle, if you're going around like a square, that's the circulation around those things. So instead of doing the circulation through a vector field, you can create a surface out of that path. Like instead of going around in a circle with your path, you can just sort of shade in the circle, and now you have a disk. Now you have a surface. So instead of doing the line integral around the circle, you can do the flux integral through the disk of the curl of the vector field. And so some of you might be saying, I don't want to go backwards. Line integrals were fine. Flux integrals are terrible. I want to do line integrals whenever possible. When we do this, it will be because these surfaces are really easy to parameterize. And a lot of time they'll just be flat. And you don't even really need to parameterize them. You just say the thing is flat, so the normal vector is 0, 0, 1. And then you're done. Step 2 of the flux integral is finished. So when we do this in this direction, it will be because finding these normal vectors is very easy, and working with the curl of the vector field is going to be easier than the original vector field itself. A lot of these vector fields clean up pretty nice when you take the curl of them. So Stokes, I've already said Stokes is between our two shortcuts, Stokes is the one is the more severe. It's got a lot of steps to it. The next shortcut we'll do in 17.8, the last section of Calc 3, that will be much nicer, much more shortcut-ish. So before we get to that, I want to do a couple examples of Stokes' theorem. I want to do an example going in each direction, and I'm going to start with the example where we go in this direction. So instead of the circulation f dot dr over this path, where f is negative 2z, 3x, and negative 5y, calculate the flux of curl of f through the disk. Oh, I should say, instead of the curl where f is that and c is the circle x squared plus y squared equals 16, z equals 0. Okay, so we have our vector field, and we have a path. So we could do the line integral where we parameterize this path and we express f in terms of this path, and then we do our dot products, and then we do the line integral there. Or instead of that, we could calculate the flux of the curl of f through the disk that this circle sort of encloses. So for this first example, I think I want to do it both ways so we can verify that this actually works. So let's start with the line integral, because that's what this is originally presented as. The parameterization of this path, this is a circle of radius 4, should be 4 cosine t, 4 sine of t, and 0 on the z-axis. So the derivative of that should be negative 4 sine of t, 4 cosine of t, and 0. When we express f as a function of t instead of as a function of x's, y's, and z's, we'll get that f is 0, 12 cosine, and then negative 20 sine. F dot dr is going to give me 48 cosine squared t. So now we just have to integrate f dot dr, which will be the integral from 0 to 2 pi of 48 cosine squared t dt. So if we're integrating cosine squared, we need to use the half angle formula where we transform this. I'm going to take cosine squared is going to be 0 to 2 pi. Cosine squared is 1 plus the cosine of 2t over 2. So the 48 is going to turn into a 24 plus the cosine of 24 plus 24 cosines of 2t dt. And now when we actually integrate that, we get 24t plus 12 sine of 2t from 0 to 2 pi. And when I evaluate the sign at 0 and at 2 pi, I'm going to get the same thing. That's 0 either way. So this is just going to be 48 pi. So line integral, not terrible. There's a lot of moving parts in here. Lots of sines, lots of cosines. We get cosine squareds. It's all right. Let's see if this looks any better when, instead of doing the circulation line integral around the edge of this circle, we do the flux through the surface of the disk. So let's see if we can make this better than it was. And we're looking for 48 pi as our final answer. Okay, if we're going to do Stokes' theorem on this, first thing we need is to find the curl of f. So the curl of f is going to be the cross product I, j, k, derivative with respect to x, derivative with respect to y, partial with respect to z, and then negative 2z, 3x, and negative 5y. This is, we need to find this curl because we're going to use the curl of this as the vector field in the surface integral, the flux integral. So expanding across I gives us negative 5. Right, there's that derivative, and that derivative is 0. Expanding across j is going to give us 0 and negative 0 minus negative 2z. So I think this is the triple negative version. J is inherently negative, the value is negative, and it's on the backwards diagonal, so it's negative. So this will be plus 2. No, triple negative is negative. So minus 2j. And then expanding across k is going to give us 3 minus 0. So plus 3k. So here's what I like about this vector field. This vector field is all constants. Variables are gone. There's no sines, there's no cosines. There's just a bunch of numbers, no variables. So that's nice. Next we need n. Usually we have to go through this pretty horrifying song and dance where we parameterize this surface and we take derivatives with respect to each variable in the parametric thing, and then we take the cross products of those two partial derivatives to get a vector that is always normal to this. But this is nice. Our surface is on the xy plane. It is flat. It means the vectors that are normal to it are just k. 0i plus 0j plus 1k. This is the normal vector. Or if you want to do these in brackets, this would be negative 5, negative 2, 3, and this would be 0, 0, 1. So a lot of times, if you're going to do this Stokes theorem thing, it is because the curl is going to give you constants, and that's nice. And it's because the normal vectors are easy, and that's nice. So when you do the dot product of this vector field, dot n, that's the dot product of this and this, that's 3. This thing that you're integrating, this surface integral you have, the double integral of the cross product of f dot n ds across this surface, this is just the integral of 3 on this area. And now we can use that neat little trick where when you're doing this, when you finish writing your flux integral, if you have a constant, you can kind of skip the whole integration thing and just say, well, if it's at this constant across this much area, multiply this constant times the area, and then you're done. We know the area of this circle. This is a circle of radius 4. So the area is going to be pi r squared. Pi times 4 squared is 16 pi. So this is 3 times 16 pi, which is 48 pi. So there's a cross product involved, and cross products are moderately involved, but once you get past the cross product, every step of this surface integral is really effortless because the normal vector is nice, the vector field is all constants, the dot product is effortless, and then when you do this flux integral of a constant, you just multiply by the area. It's pretty great, actually. I think this is easier. I think the Stokes theorem version of this problem is easier than the line integral version of this problem. I mean, raise your hand if you remembered the half-angle formula for cosine. Maybe. I like this better. I have one more video coming on Stokes theorem, so this will be part 1 here. I'm going to do another video that will be part 2, where I'm going to do another example. The other example, I'm kind of going to go in the other direction. So instead of doing the surface integral of the curl of the flux, we're just going to do a line integral across the edge or around the edge of the surface. So yeah, stay tuned for that. That one's coming.